Good day, everyone, and thank you for joining us. Today, we're going to be looking at recyclers with chemical reactions. So, this is the problem statement that we're given. Let's just go through it, and after that, let's solve the problem step by step. Now, it's very important that you take note that in most cases, when you're given a chemical reaction, you will even be given the chemical reaction equation. In some instances, when you're not given, you might have to write it down if it's a simple one. Okay, so ethyl ethyl is made by the dehydration of ethyl alcohol in the presence of sulfuric acid at 413 kelvins. Now you're given the reaction equation like I've just stated there. You can see that your product is the diethyl ether and you also have H2O. Okay, and then obviously your raw material being the ethanol. So in this figure here, it's a simplified process diagram. You can see that 87% conversion of the alcohol fed to the reactor occurs per pass. So the single pass conversion in the reactor is only 87%. Okay, and then you are required to calculate the kilograms per hour of fresh feed, and you also required to calculate the kilograms of the recycling stream. So what is it that you have to calculate? That's very important. So you can highlight here. So this is the fresh feed that you're supposed to calculate. So F here, the fresh feed, and you're also supposed to calculate the recycling stream. Okay, the kilograms of that. So once you figure that out, then you are sorted. So you've already answered the question. Okay, so how do you go about doing that? You can see that here they say pure ether is 1,200 kilograms per hour. So now that's very key because that's what you need to use as your basis because that's the only amount that you are given. The others that you're given they is composition and it's on a mass percentage because these are liquids. Okay, so you're working with liquids here. So now your basis there, you just write it down. My basis is 1,200 kilograms per hour of diether. Okay, or you can just save ether. Makes it more simplified. And then now you can move on. Just bear in mind what is it that you're looking for. You're looking for the fresh feed. I've denoted with the question mark. F equals to question mark and R equals to question mark. So it's the fresh feed and the recycling stream. So now that you've given your basis, you can go now and write down your chemical reaction equation. But you can just first convert even your bases into moles because when you're using the chemical reaction equation here, the chemical reaction equation always requires that you use molar ratios if you have to determine the other values. So you must make sure that everything is in moles. Okay, so now I can see the diether produced there. The diether that is produced, say 2. So there we go. Okay, let's look at the diether that is produced there. And then, okay, so the ether is produced here is C2H5O C2H5. Okay, so that's the empirical formula. And then mass over molecular weight. You just need this in moles. So you know the mass, it's 1,200. And now if you calculate the molecular weight, it's 4. And that gives you how many moles? It gives you 16.216. It's important that you round off to the nearest, rather 3 significant figures. So this is kilogram mole. Okay, this is kilogram mole. Now because here I just ran short of space, I can even leave it as mole. So here you've got mole. Okay, so now what follows next is writing a balanced reaction equation. So this is your balanced reaction equation. So you see 2 H5OH, that's your ethanol, gives C2H5OC2H5, that's your ether plus water. Okay, so this is your chemical reaction equation. Now, because this is the product, you can actually use stoichiometric molar ratios to determine the other. So here you've got 16.216 is to 1, which is 2, which is 16 as well. So this one here is also 16. So you've got 16.216, and then is to 2, which is 32. You punch from your calculator. Just use the molar ratios. That's why it's important for you to convert to moles. Okay, so these are the moles reacting. Okay, so what you have here is the moles reacting. You have the moles reacting, and then on the other side of the equation you've got the moles produced. So now, since we know, there's no alcohol produced at the end of the process, now let's go back to the diagram so you can see what I'm talking about. It's very important in recycling systems to monitor the diagram or have a detailed study of the diagram. You can see here that there's alcohol coming in the system, and then at the end of the process there's no alcohol that is there. It just shows you that all the alcohol that came into the system reacted on an overall to its maximum capacity, of which means at the end of the process there's no alcohol. Okay, so you do not have alcohol produced here. Alcohol produced is not there. So that simple tells you that you can assume that your overall conversion is 100%. Okay, the fact that there's no alcohol produced, it means all the alcohol that came into the system reacted completely to be transformed to the ether and H2O. So now here, since there's no alcohol in P or in the product, you can assume that the overall conversion, OA, is 100%. So the overall conversion is 100%. As simple as that. So now what's the conversion? So percentage conversion, if you're looking for the overall, percentage conversion is given by, in this case, is the ethanol. So C2H5OH that reacts overall divided by C2H5 that is fed in the fresh feed. So this is the fresh feed. Okay, so now the fresh feed, this is the fresh feed, is that F there. So that's the fresh feed. So the alcohol fed in the fresh feed there. Okay, that's what we're utilizing. Okay, so now what we need to find is the alcohol that reacts. Okay, remember this is always multiplied by 100. Okay, so now if we have to find C2H5OH that is actually fed, because that's what we're looking for. Yeah, if we go back to the question, it's important to always give it kilograms per hour of fresh feed. The kilograms per hour of fresh feed. So we're looking for fresh feed. Okay, so let's proceed. So now in order for us to get the fresh feed of alcohol as a component first, C5OH. Okay, yeah, that is OH that is fed is going to be given by, okay, it's fed in the fresh feed. So write it down so that you know exactly what is it that you're looking for. Okay, so now in the fresh feed you've got 32, okay? 32, because that's moles reacting, so it's 32.432. Now because we said all the alcohol reacts, so the 32.432 moles is the same as 32.432. Those are the moles of alcohol in the fresh feed, not the fresh feed stream, but the moles of the alcohol in the fresh feed. Okay, so now since we have this ethanol in the fresh feed, we can convert it to a mass. Okay, so ethanol in the fresh feed, you can write it like that because it's F. That's your ethanol in the fresh feed, 2.432 multiplied by the molecular weight of the ethanol, which is 46, and that gives us, what does that give us? Let's just remove that. Okay, so that will give us 1491. You punch in our calculators, 1491.872. now these are kilograms per hour, okay, of ethanol fed. Okay, that's the ethanol in the fresh feed. So now in order for us to get the total fresh feed stream, since we know that it's 95%, that's what we given, the 95% of the fresh feed is ethanol, which is C2H5OH. It means that 95% of the fresh feed is equivalent to 491. You just use the correlation. Okay, so now that will simplify to, when you punch it in your calculator, it will simplify to 1570.4. Okay, this is kilograms per hour. Yeah, so you should take note. This is what's desired, the total stream of the fresh feed. And you must take note that these percentages are mass fractions. That's why we had to first convert everything to mass first before we get the final answer, which is 1570.4 kilograms per hour. So that's the total feed stream. So now let's go now and find the recycle stream. Now finding the recycle stream is easy because we've assumed an overall conversion of 100%. So you just employ this correlation, signal pass conversion divided by the overall conversion, and then the fresh feed of that particular component of utmost importance. In this case, it's ethanol, divided, okay, by fresh feed of that particular component plus the recycle of the component of utmost importance, which is ethanol. It's our main component in the feed stream. That's the one we use to measure the conversion. Hence, we say it's a component of utmost importance. Now, you can just quickly substitute 0.87, which is the signal pass conversion, and then this one is 100%. So, which means it simplifies to 1. Okay, sorry about that. It simplifies to 1. Okay, and then here you've got 32. Make sure that everything is in moles because you're still working with moles. Okay, and then there you've got 32.432 plus the cycle, what you are looking for, C2H5OH. Okay, so you can make your division line a bit longer. So now what's your unknown? The recycle stream. Okay, so now here you get 4.85. Okay, so you can easily convert to mass by multiplying with the molecular weight, which is 223. This is 223.1. Okay, now that's kilograms per hour. Okay, so now when it's like that, then you can easily use the correlation. Okay, because now it's very simple. The ethanol in the recycle stream, let's just go and look. You see the recycle stream there in the problem statement. The ethanol or the alcohol is given as 92%. So we use that now since we've got mass now. So it works very well. So you can see now 92 0.92%. Okay, using the mass fraction, so it's 0.92 multiplied by R gives us 223.1. So which means R, or the recycled stream, is given by 242.5 kilograms per hour. Okay, so that's the recycled stream. Okay, so you have your recycled stream, and then you also have your fresh feed. This is your fresh feed. Okay, and then you've got your recycle. So we've answered the question. If we go back, what was required was to find the kilograms of the fresh feed and the kilograms of the recycle. So we are done with the question. Thank you very much for watching. Let's keep on enjoying chemical engineering. See you next time.